what is COFFIES? COFFIES is one of the nine NASA-funded heliophysics Phase 1 Drive Center, and we are working to establish multi-institutional collaboration to develop the most reliable data-driven physical model of solar activity. So COFFIES stands for consequences of fields and flows in the interior and exterior of the sun. We have a website, coffees.stanford.edu, and for any outsiders, you can go there to look at more details about our center. Okay, so let me introduce our speaker today. Travis Metcalfe is from Space Science Institute is going to give us a seminar today, and he earned his PhD from University of Texas at Austin, where he studied white dwarf astroseismology. He built his own specialized Linux cluster and developed an early machine learning method to squeeze precious information out of the data. He held postdoctoral fellowships at Aarhus University in Denmark and then at the Harvard Smithsonian Center of Astrophysics, where he extended the method to sun-like stars. He joined HAO from 2004, first as an NASA fellow and then as a staff scientist in 2006, before moving to Space Science Institute in 2012. Travis is now a senior research scientist at White Dwarf Research Corporation, a non-profit organization that he started as a grad student. He is currently leading a project that combines spectral polarimetry from Large Binocular Telescope in Arizona with astroseismology from NASA's Transiting Exoplanet Survey satellite. Okay, so let's welcome our speaker and thank you in advance for giving the seminar. So you probably can start now.
Okay, thanks so much for the invitation. Really appreciate it. I've never actually visited Stanford before, and I still haven't, but but I hope to do so sometime in the future when things open up again. All right, so why don't we start by looking at the sun. If you were to observe the sun as a star, then you would measure its its stellar activity cycle as being between 10 and 11 years. And you'd measure its rotation period to be between 25 and 26 days. But what's the relationship between these two quantities? That's something that dynamo theorists might want to know. And with a single data point, you really can't say anything. But as soon as you add the context from other stars, the picture becomes quite interesting. From the perspective of stellar astrophysics, it's interesting because whatever circumstances lead the sun to be in this sort of unusual position in the diagram, we have the luck of having a front row seat that will allow us to characterize those circumstances in extraordinary detail compared to anything we could have access to for other stars. From the perspective of solar physics, it's interesting that because whatever creates the order that is apparent for these other sun-like stars, whatever creates that order could be distinct in some important ways from the order that we observe in our own star, right? So it might make sense to see whether we can reproduce these general characteristics of the relationship between activity cycle period and rotation period before we try to match the particular case of the sun. So there are apparently two distinct relationships between rotation period and activity cycle period. And in the range of rotation periods where the two sequences overlap, stars actually show cycles on both sequences simultaneously. So when Erica Bonvitens published this figure in 2007, she suggested that these two sequences actually represent two independent dynamo mechanisms operating in different regions of the star, where this upper sequence would be a dynamo driven in the shear layer, in the near surface shear layer, And this lower sequence would be a dynamo-driven by the shear layer at the base of the convection zone at the tachocline. Okay, so over the past 5 years, we've developed a new understanding of magnetic evolution that we think can explain why the sun is in this unusual position in the diagram. So we'll come back to the diagram later in the talk. But I'll start by sort of reviewing rotational evolution and how it connects to the evolution of chromospheric activity. I'll then outline our current best understanding of the physical mechanisms that drive the unexpected behavior that we've found recently. And I'll finish with the latest results from recent observational tests of this new picture. Okay, so the story of rotational and magnetic evolution really starts almost 50 years ago with this paper from 1972 by Andy Skumanich. And what Andy did was measured rotation in the form of the V sin I in spectral lines, activity in the form of calcium H and K emission. And he did so for a series of young clusters where you know the ages from isochrome fitting, and for the sun on the right side of the diagram. So just for a few young clusters and the sun, what he noticed was that rotation seems to slow over time and activity seems to get weaker over time, both of them in tandem as the square root of the age, roughly. And so these are known now as the Skumanich relations. Now, fast forward 40 years, and the picture is a little bit more complex, but the same basic picture prevails. What we've basically done is filled in some of the details at the very earliest times. Now, this is a log scale for the age here to stretch out the earliest times, and I've switched from rotation to angular rotation frequency instead of period. Okay, so the new picture as of 2008 is that stars are born with a range of initial rotation rates. So each of these cluster of points is a bunch of stars in a single cluster at a single age. So you got several different clusters at different ages, and over here the sun. So stars are born with a range of initial rotation rates. They spend a few million years with their rotation locked to the protostellar disk before they contract onto the main sequence and spin up slightly. And then from there, the dominant mechanism for changing their rotation over time is magnetic braking. So this is where charged particles in the stellar wind travel out to the Alfvén radius and shed angular momentum. And this process depends strongly on the rate of angular momentum loss depends strongly on the angular rotation rate itself. So stars that are initially rotating more quickly also lose angular momentum more quickly, while those that are initially rotating more slowly don't lose angular momentum as fast. And this process of magnetic braking leads to convergence to basically a single rotation rate at a given, for a given mass by about 500 million years for stars like the sun. And this black arrow is sort of the Skumanich relation that kind of tracks the mean rotation rate of these young clusters and then goes through the sun. So the important thing to note here is that as of 2008, we basically had no calibration points for this, no clusters older than about 1 billion years, nothing up to the age of the sun, and certainly nothing beyond the age of the sun. And so there were this is just an empirical relation, the Skumanich relation. And so without those empirical data to constrain the method, everyone just assumed that this spin down continues indefinitely. But then came NASA's Kepler mission. And just to summarize what it did, it was launched in 2009, and it stared at this one patch of the summer Milky Way for about 4 years, taking regular measurements every 30 minutes of hundreds of thousands of stars. And in some cases, at a higher cadence of a 1 minute sampling so that you could do astroseismology. And those sort of data exist for a couple thousand stars in the Kepler field. And its main focus was to search for extrasolar planets, looking for the tiny dips in light as properly oriented planetary systems pass in between us and the host star. But by design, only a few % of stars will have planetary systems that are oriented correctly to see those transits. The other 97% of stars are just great for stellar astrophysics. After that initial 4-year survey, Kepler transitioned to observing a series of fields in the ecliptic plane where there are a lot of young clusters, some of the clusters that we'd studied previously that calibrate the Scumanich relation, but for shorter periods of time, typically a few months in each of these fields. I'm going to focus on the results from the main mission. So because it's looking for, basically, it was looking for Earth-sized planets around sun-like stars, you needed the photometric precision to see very tiny shadows in front of the host star. And that precision gave you the sensitivity to detect also tiny star spots, even in stars that are as inactive as the sun. And as the star rotates, those star spots rotate in and out of view, and you get a modulation in the light. Here, the full scale is 0.1%, plus or minus. And so that exquisite photometric precision stretched over several years allowed us to measure quite easily rotation in inactive sun-like stars. In addition, that higher cadence data that I mentioned allowed you to do astroseismology, so to detect solar-like oscillations in other sun-like stars. So this is basically acoustic noise generated by the churning of convection in the near-surface regions, generates sound waves at basically all frequencies, or a broad range of frequencies. Some of those frequencies are resonant inside the spherical cavity of the star and set up standing waves that you can observe as parts per million brightness variations on timescales of a few minutes or longer. And those of you who were around in solar physics in the 1980s, if I told you this was the first detection of solar-like oscillations in the sun, you might believe me. That's sort of the kind of quality of the data from those early detections of solar-like oscillations. Right, you're basically only, because you don't have spatial resolution across the surface of the star, you're only sensitive to the lowest degree modes, so the radial modes, dipole, quadrupole, and in some cases octupole modes. In this case, you do see those. So this is actually the old solar analog 16 sig A. And the main features of this kind of data is that you see a typical frequency of maximum power. So there's a sort of comb-like pattern with a peak at a nu max, and nu max basically traces the surface gravity of the star. If you look in detail at the comb-like pattern, you actually see that it's a series of regularly spaced peaks, but interleaved regularly spaced peaks. And that characteristic spacing is the frequency spacing between consecutive radial overtones of the same spherical harmonic degree. So here, the consecutive radial overtones of 2 radial modes. And that basically tells you something about like the mean density of the star. And finally, if you have sufficient frequency resolution, which you do for these long time series that Kepler produced, you can actually resolve the tiny frequency difference, a few microhertz, between the radial mode and a nearby adjacent quadrupole mode. And basically the reason why those frequencies differ is that a radial mode travels straight through the center of the star, whereas a quadrupole mode will turn around before it gets there. And so the difference between those frequencies tells you something about the sound speed in the core of the star. And that, of course, changes over time as the star converts hydrogen into helium. And so it's a good proxy for the stellar age. And so this small delta nu 02 gives you an indication of the stellar age. Okay, so Kepler produced these exquisite data for rotation exquisite astroseismic properties where you could match these individual frequencies. You could, in principle, just use these global properties of the oscillations to get an idea of the mass and the radius and the age. But if you do some detailed stellar modeling to try to match the individual frequencies, you can get an improved precision on all those stellar properties, typically by a factor of 2. And you can measure the radius to a few percent, the mass to about 5%, and the age to 10 or 15% in the best cases. So combining those measurements of rotation with those basic stellar properties, in particular the age, allows you to get some new data to understand what happens with the Skumanich relation, the one for rotation in particular, at a broader range of ages than was possible before. And when you look at those data, those sort of data don't exist for a large number of stars, just a few dozens. Some of them very sun-like and others hotter, others cooler. But what you find is something unexpected. So this, I'm plotting the rotation period, increasing downwards, you're welcome, versus the astroseismic age. And so the dark solid line here shows standard spin down, where it's like a Skumanich law that's been calibrated using young clusters and the sun. So constrained to pass through the sun as a standard model. These colored lines are modified models to try to explain these new observations. So for the first time, we obtained reliable rotation rates and ages for stars beyond the age of the sun. And rather than following, so the younger stars follow the Skumanich spin down relation just fine, but somewhere around middle age, stars begin to deviate from this relation. And what it looked like is that their rotation rates stay almost constant during most of the second half of their main sequence lifetimes, until they begin to expand as subgiants. And then the rotation rate continues to change just from the change in the moment of inertia as the star expands. Kepler observed this in sun-like stars, but also in hotter stars. And the point at which the stars appeared to deviate from the standard spin-down relation appeared to be at a constant Rossby number. Okay, so the Rossby number is the ratio of the rotation period to the convective turnover time. And since hotter stars have thinner convection zones, they have shorter convective overturn times. And so you reach a critical Rossby number at faster rotation, earlier age than cooler stars like the sun. So this was a Nature paper led by Jennifer Van Saters in 2016. And so these colored curves are her modified models where she fits for a single parameter the value of the critical Rossby number where stars stop slowing down, stop following this standard spin down relation, and is able to match all of the observations when the critical Rossby number is pretty comparable to the Rossby number of the sun. So somewhere around middle age, stars appear to stop spinning down. That is a puzzle. And it's not just for this really well characterized sample of stars with astroseismology. If you just look at the distribution of rotation periods for all stars in the Kepler field, so this is a sample by McQuillan et al. In 2014, containing rotation detections for something like 35,000 stars. And there's this peculiar edge in the distribution where the density of detections falls off. Now that's kind of 90% of the stars in a given temperature band are below the black line. That's how the black line is defined. So that's kind of that edge observationally. It deviates from what your eye would say it is over on the left because of blends. Kepler had slightly large pixels. And so you can have a hot star that dominates the light. And so your determination of the temperature blended in the same pixel with a rotation signal from a much cooler star. And those stars typically rotate longer, take longer to rotate. And so you deviate due to blends over on this side. Now, if you can basically generate a galactic stellar population model for the stars in the Kepler field and ask, what should this distribution look like if they all obeyed the Skumanich spin-down law? And that is the red curve. So there are a bunch of stars missing, sun-like stars with long rotation periods are not there. I mean, and that's just another way of saying what we already discovered from this small sample of astroseismic targets. But importantly, with her weakened braking model, she was able to reproduce this edge pretty precisely. And that was a follow-up 2019 paper. So either stars spin down until they get to this critical Rossby number and then hang out there, or something happens to their activity to make it undetectable beyond that, and we just simply don't detect those stars anymore. Most of the background here, the smattering of points at longer periods, are subgiant stars that have evolved. So like these have evolved from over here and are on their way up. Okay, so at this point, you might be wondering, all right, fine, but does this have anything to do with the sun? And the answer was provided recently in this series of papers by Adam Finley and collaborators, where they asked, what is the current angular momentum loss rate for the sun? And they did so initially from observations at 1AU from the WIND spacecraft over a full solar cycle, actually more than a full solar cycle. And more recently, from the first couple of encounters of the Parker Solar Probe. And in both cases, the answer was qualitatively very similar. And that is summarized by this quote from the first paper, that the angular momentum loss rate, the current angular momentum loss rate of the sun, is a factor of 2 weaker than is required to sustain a Skumanich-like rotational evolution. So it does seem to be true that the sun is not losing angular momentum as quickly as we would predict if we think it is currently obeying the Skumanich spin-down law. So it does seem to have something to do with the sun. Okay. All right. Okay, so now I'm going to transition to talking a bit about activity, because at least in the first half of main sequence lifetimes, rotation and activity are strongly coupled. And so we can ask, what's the relationship between rotation and activity at these later phases of stellar evolution? And so the traditional proxy that people use to characterize magnetic activity in sun-like stars is the calcium H and K emission. So this is chromospheric emission. You can see when you compare an image of the photosphere and an image of the chromosphere that this bright, so this is an image in the calcium K line, and you get bright regions around all the spots, but also this whole network of magnetic network in the background that traces the overall magnetic activity level. And so that's why calcium H and K emission is used as a proxy. So basically, it's a proxy for the strength and filling factor, some combination of those things. And typically the way that stellar astronomers measure this is through a relative measurement of emission integrated in the line cores of the H and K lines relative to these nearby pseudo-continuum bands to the red and to the violet. And so alpha here, so this is the so-called S index that was measured by the Mount Wilson Observatory over many years, starting in the 1960s. This alpha is a calibration constant so that you can calibrate, anybody with measurements that are not from the Mount Wilson Observatory can calibrate their measurements to the same scale. And an important additional measure is the so-called R prime HK, and it takes into account the fact that the emission that you get is a function also of the mass of the star or the spectral type of the star. And so if you want to compare a sample of stars that are not all the sun or not all exactly one solar mass at the solar age, you need to correct for the fact that the luminosity of stars are different for different masses and different ages. And so that's what R prime HK does. You multiply the S index by some function of the color, which is really a proxy for the mass or the temperature, and then subtract off a photospheric contribution to the emission in the calcium H and K lines, which is also depends on spectral type, and that's determined empirically. So R prime HK is basically the flux in the calcium H and K lines relative to the bolometric flux of the star, bolometric luminosity of the star. Okay. All right. So as I mentioned, the Mount Wilson Observatory performed a really well-known survey for magnetic activity cycles in other stars starting in the 1960s. And this is just a sampling of some of those, the best results, excellent cycles from that survey. And so, the first thing that they essentially discovered was that, yes, other stars like the sun have cycles the way the sun does. But that the length of those cycles varies. In these examples, there are anywhere from 7 years to 16 years, where the sun is at 11. In the full survey, they detected cycles anywhere from 2.5 years was their shortest, and 25 years was their longest, and that was basically limited by the length of their data set. They stopped observing in 2003 after nearly 30 years of, or a little more than 30, nearly 35 years of observations. Okay, so these sort of cycle detections are what went into that Bonne-Vitesse plot that I showed you at the beginning. And just as a kind of side note, the Mount Wilson Observatory also actually toward the beginning and toward the end of the survey made measurements, regular measurements with the same instrument of the sun through reflected moonlight, right? They observed the moon so that you could cross-calibrate these instrumental measurements with the background here in the top panel is the Kitt Peak calcium K measurements. It started in, I guess, the late 70s. And these earlier measurements are from Kodaikanal in India, I think. So you can basically calibrate those earlier measurements and these more dense measurements from Kitt Peak to the Mount Wilson scale and be able to place the sun on the same instrumental scale that they observed all these stars in. So that's an important fact. And this was work published a few years ago by Ricky Egeland as part of his PhD thesis. Okay, so when you look at the chromospheric activity level, so now this is that log R prime HK, where you can compare stars with different spectral types and ages versus rotation period. The colored points here are from the Kepler sample, and the little stars are from the Mount Wilson sample. But I want you to focus on the connected series of points here. These are a series of solar analogs, so from the youngest down to the oldest. And basically what you find in all these samples, but it's very apparent in these solar analogs, is that somewhere around the activity level of the sun, rotation and activity decouple. Right, so you get the standard schematic spin down, rotation is changing over time, activity is changing over time, they're doing so in tandem. But around the activity level of the sun, rotation essentially stops changing, but activity continues to decline. So from 18 SCO, which is about 4 billion years old from ground-based astroseismology, Alpha Centauri, which is about 5.5 billion years old, and 16 Sig B, which is 7 billion years old. So activity continues to decline even though rotation stops changing. Okay, that's interesting. How about in the activity cycles? Now, this is an updated version of that Bohm-Vitens plot that I started with. And I've done two things here to update it. One is that I've color-coded the points by the temperature of the star. And so the sort of yellow points are solar analogs, blue points are hotter stars, and red points and orange points are cooler stars. And then I've added along the top a few of the stars from Mount Wilson, from the Mount Wilson survey, where they were able to measure the rotation rate. So you can still measure chromospheric activity and it modulates with the rotation. So you were able to precisely measure the rotation rate, but the star just stays at the same activity level over decades. So they call these flat activity stars. So there's no cycle, and it's kind of like a lower limit to the cycle length. It's got to be longer than 25 years, the length of their survey. So I've just added a few of those where you could measure rotation, but there's no cycle, okay? Now, here's our revised picture of the evolutionary paths of stars in this diagram. And this is driven by the same series of solar analogs, 18 SCO at 4 gigayears, alpha Cen at 5.5, and 16 SIG at 7. So that series of solar analogs clearly seems to show that once stars reach this critical Rossby number and their rotation rate stops slowing down over time, the cycle period appears to grow longer and weaker. The alpha Cen A cycle is quite weak. It's only measured in the X-ray before disappearing entirely. 16 SIG is measured to be a flat activity, constant activity star over a couple of decades. But you can find examples in the Mount Wilson survey that are both hotter and cooler, where you have stars that are similar in rotation period, but have activity levels that are on opposite sides of this apparent transition. So it appears to be the case that, that coincident with this cessation of magnetic braking, you have a fundamental change in the character of stellar activity cycles. Okay. All right, so what's going on here? What can the stars tell us about how we can understand what's going on? Well, it's a four-part argument, and so I'll just give you our current best picture of what might be happening to make this this magnetic transition take place in sun-like stars. So the first thing is that as rotation slows down, it's harder and harder for Coriolis force to be imprinted, Coriolis forces to be imprinted on the global convective patterns, right? In very young stars, you have kind of complex rotation in this sort of Taylor-Proudman state, kind of a cylindrical rotation. But as the star slows down, you approach uniform rotation, or theoretically, it could be anti-solar differential rotation, where you have a slow equator and fast poles, but there's not a lot of observational evidence for that. So we think fundamentally, it's that slow rotation becomes non-differential, and there's evidence for that that I can show you at the end if you want to ask during the question period. Now, if you eliminate differential rotation, you basically lose the shear that is driving part of the dynamo loop. So you disrupt the omega effect that is responsible for converting poloidal field into toroidal field, right? So because of differential rotation, red is fast and blue is slow. If you take a global dipole field like this, that differential rotation will wind it up over time and generate toroidal field at the base of the convection that rises up to the surface, emerges as active regions, gets shredded by convection and redistributed towards the poles by meridional circulation to recycle the large scale field. If you lose that shear, if your differential rotation begins to break down, you're basically severing the dynamo loop, and you lose your ability to regenerate that large scale field. Now, that's important because in the current context, because the rate of angular momentum loss depends strongly on the geometry of the field. And in particular, the dipole component of the global field is responsible for something like 80% of the angular momentum loss from the stellar winds. So the color scale in the background is a measure of how much angular momentum is the angular momentum content of the stellar wind, with red being a lot of angular momentum and blue being not so much. And the dashed white line here is the Alfvén radius. And so charged particles are entrained in the magnetic field out to the Alfvén radius, and that's where they break free of the magnetic field lines and shed that angular momentum. And so since the Alfvén radius is so much larger for the dipole field than it is for higher order fields, it just starts snugging in closer and closer to the star as the geometry gets more complex. Almost, a very large fraction of the angular momentum loss is due to the dipole component of the field. And so all you have to do is get rid of the dipole component of the field to effectively turn off magnetic braking, or to make it dramatically less efficient. And we think that this is basically represents the shutdown of the global dynamo, driven initially by the loss of differential rotation. But we definitely know empirically from the Mount Wilson survey that this is true. Young solar analogs, have a high level of mean activity, a large degree of variability, and complex variability that's multi-periodic. But as a star ages, its average activity level comes down, its variability decreases until, around the age of the sun, it becomes very well ordered and monoperiodic. But then beyond the age of the sun, it eventually reaches this constant activity state. So these flat activity stars that are in the Mount Wilson survey. And there's still magnetic flux there to measure. You can measure these calcium H and K emission. So there's still flux there, but we think that it is just the remnant of a small scale local dynamo that continues to evolve over time. But the global dynamo breaks down shortly beyond the age of the sun. Okay, so the best picture that kind of synthesizes all of these observations into a coherent storyline is this picture put forward by Cecilia Garofalo and collaborators a few years ago, that all of this is driven just by the evolution of magnetic complexity, and that there are kind of three regimes in the evolution of a sun-like star. So very young stars, sorry, let me explain what the axes are here. This vertical axis is, you can think of as it's a magnetic complexity parameter, but you can think of it as the mean spherical harmonic degree of the global magnetic field, okay? And in very young stars with Rossby numbers smaller than about 0.1, you're in the saturated regime where you've just squeezed as much magnetic flux on the star as you possibly can. And the magnetic field is extraordinarily complex, but gradually becomes more ordered over time until you reach the schematic. You turn on a global dynamo, generate a dipole field, and then you're in the Schumann regime. That dipole field effectively couples rotation and activity beyond that saturated regime out to a Rossby number comparable to where the sun is now. And then the complexity of the magnetic field appears to get more complex over time again. And again, you lose that coupling between rotation and activity. And it's all driven by the loss of the dipole large scale organization that the dynamo naturally produces, but at some point loses the ability to sustain because of the loss of differential rotation. Okay. So that's the big picture. If if that turns out to be true, then there's a very specific prediction that if you compare stars that are clearly in the schematic regime, showing clear cycles, if you compare that to a star that's, say, a flat activity star that you think is over here in the more complex region, you should easily detect a dipole field in these more active stars, and you should not be able to detect it in more evolved stars, these stars that appear to be beyond that transition. So the tool of choice for making those kind of measurements is spectropolarimetry. Now, solar physicists think of spectropolarimetry a little bit differently than stellar astrophysicists do. We don't have any spatial resolution. And so spectropolarimetry is effectively a spatial filter that allows you to detect or not the presence of large-scale magnetic field. Because of geometric cancellation effects, the technique is most sensitive to dipole field and progressively less sensitive as you get a higher degree of complexity. And beyond a spherical harmonic degree of about 5, there's no hope in detecting any smaller scale surface features without spatial resolution. And just to give you an idea of how the sun would look if it were measured as a star in spectropolarimetry. So typically what is done is here's a Carrington map of spectropolarimetry for the sun, and it's decomposed into radial, meridional, and azimuthal components. But it's dominated, the strength is dominated by the radial component. So this is the actual observations on the top. And if you decompose that map into spherical harmonics and then reconstruct the field using truncating the spherical harmonics at a degree of 150, you get out basically what you put in, okay? But if you truncate it at a spherical harmonic degree of 5, which is sort of what we can do for other stars, then you get this sort of blobby looking thing in the middle. So you basically only see large scale imbalances between the distribution of oppositely directed polarities, okay? So this is the kind of map that you can get for sun-like stars. And you can see that if you observe it at a particular rotational phase, you might get complete cancellation of those small scale features. But at other rotational phases, there might be a dominant polarity of one flavor or another that allows you to detect that field. So you have to be a little bit careful, but all right. So we went to the Large Binocular Telescope in 2019 and tried to measure the large scale field for a pair of stars that were on opposite sides of this transition, the hottest, more rapidly rotating stars in our sample. Let me just quickly remind you, it's these two stars here. So active star on the normal sequence, inactive flat activity star that appears to be at the other end of that transition, okay? And what did we find? Here's the results of those measurements. So in the more active star, we easily detected a non-axisymmetric dipole field with a average line of sight strength around 2.5 Gauss. Okay, so that's this one here. And we know from long-term observations at Mount Wilson what the relative activity levels of these stars are from the chromospheric activity measurements, right? So chromospheric activity is not sensitive to polarity. You're just integrating the magnetic flux on all spatial scales. And so by comparing the relative activity levels in calcium H and K, you know that this inactive star should be about 3/4, should have a magnetic field that is about 3/4 as strong as the one that we observe here. But if you just scale that signal down by 3/4, I think you can see that we did not detect it. In fact, we can set upper limits on the strength of a dipole field to be less than 20% as strong as this one. And if it's quadrupole field, because there's more geometric cancellation, you can put a stronger field in. It can be no stronger than 53% as strong as this one. So
Travis, sorry, what is the age of this star?
What is the age of this one?
The right, yes.
Yeah, we didn't know at the time. Previously, people had estimated its age from its rotation period, which is exactly the wrong thing to do if it's no longer obeying spin down, to be 2.5 billion years. This is about 2 billion years, 88 Leo. Rho Corridor, we have since done astroseismology from the Transiting Exoplanet Survey satellite and measured the age to be about 10 billion years, just shy of 10 billion years. So it's quite old. Yeah, so it all kind of holds together. You don't detect a dipole field in this star that we think is beyond the transition where spin down ceases. And it's an old star, consistent with its activity level, in fact. So we think this is the first confirmation of the theory. And what we're going to do now is go back and perform the same test for sun-like stars and cooler stars to see like basically pairs of stars where you believe you can make the detection in the more active star. So you know that your non-detection in the less active star is because there's no field there, not because you couldn't detect it, right? We establish the detectability using the more active star and then show a significant absence of a detection in the less active star. And so we're hoping to continue these measurements for a sample of about a dozen benchmark stars where we can combine these kind of measurements with precise ages from tests and piece together this picture of magnetic stellar evolution. Okay, so with that, I will put up a summary of my conclusions and maybe take some questions.
Hi, Travis. I have some questions and some comments too.
Okay.
So the picture of P-rod versus P-cycle, many people have worked on this data, and results from Olspert in 2018 show that basically the active branch doesn't exist. It shows that the active branch may appear like with the same inclination, but there is a transitional branch, and then merging with the superactive branch, everything is below this data. So what do you think about that? You seem to believe that it's consistent, right?
Well, I'm agnostic about the existence or non-existence of the active branch. In fact, none of what I've just described depends on its existence.
But this transition towards the active branch is not an evidence for you?
No, because these are a different dynamo. If you believe that these cycles exist, and then they represent a different dynamo because there's a relationship between basically because there's a different relationship between the number of rotations per cycle, right? And so it's like a different dynamo number.
But anyway, if what you are saying is correct, then you will see more stars close to the active branch and not in this transitional branch. The transitional branch is more active. And basically in the data reanalyzed by Olspert, and also for I think Diego Lorenzo is also doing things like that. The active branch or stars above the inactive branch, basically there are very few. in these positions where you have 18 SCO and Alpha Centauri A.
Yeah, so Alpha Centauri A, this cycle clearly does not belong to the active branch. Just based on all of its characteristics, it's not even visible in the calcium H and K. I've got a time series of H and K observations for Alpha Cent A, and it is extremely low amplitude. It would not have made the cut to be on this plot for Bonvitens. She only plotted cycles with the most secure detections. So no, I mean, I think this transition happens kind of independently of the existence or not of that, because this is a transition in this dynamo, in the lower sequence of dynamos, right? If you believe in the active branch, okay, then there is also a simultaneous transition of that cycle upward at the same time. It just becomes intractably long that current decades of observations are not enough to see it. So if the transition happens for one of the dynamos, it probably happens for both of them. If it's, if you're just getting rid of differential rotation, then both of those cycles are going to evolve simultaneously. But we're just focusing on this bottom sequence because A, it's more secure, everybody believes in it, and B, it appears to be where the sun came from, if this picture holds up, that the solar cycle has evolved from shorter periods in the past. So for example, 18 SCO, which is long been studied as a solar twin, but its cycle is only 7 years. And this helps make sense of that puzzle as well.
Yeah. Go ahead.
If that's a follow-up to the current question, then you can go ahead. But I was just going to say, Irina's got her hand raised, so.
Hello? Can you hear me?
Yep.
Okay, thank you, Travis. Excellent presentation. My question regarding stellar companions, because I see you have like 16 Cygnum and the Alpha Centauri A. So it presence of companion can affect, of course, on evolution of rotation rate, right?
Sure, yeah.
This into account because it's kind of tricky thing, I assume.
Yeah, certainly for the Kepler sample, we've already screened out all of the stars with spectroscopic companions, close companions especially. I mean, Alpha Cent A and 16 Sig, those are both really wide binaries, right? So you wouldn't expect, they're effectively isolated stars. They're evolving as single stars. That they're not close enough to have an influence there.
Okay, thank you. I have additional question. What I always have a concern about such type diagram which show like active and inactive branches, and we have the sun just in the middle, right? But as you said, like interpretation is two different dynamo types corresponding to each branches. But actually, as we know, it is not just, we have range of lengths of solar activity cycles, and same thing for rotation rate. It depends, can depend from latitude. And it means even within this picture, sun will start to move sometimes closer to active branch, sometimes to inactive branch, and probably kind similar thing exists for stars. We just cannot distinguish probably variations, of course, in rotation rate and length of cycles, because irregularity of cycles, for example, for young stars.
Sure, like, so for the sun, in the modern record, there are cycles that range from, 9 to 14 or something, right?
Yeah.
So there's a big range there that we may not have captured for other stars because the data sets are only a few cycles long. I think that's part of your point, at least. But on the rotation question, let me show you one additional piece of evidence for this picture. Yes. This is a paper led by Othman Benamar in Science from a few years ago, where they actually measured the rotation rates of, not just the rotation rates, but the latitudinal differential rotation. They tried to detect latitudinal differential rotation for Kepler astroseismic targets. And basically the thing that makes that possible is if you look at the quadrupole mode, it's a quintuplet. And the sectoral modes are basically sample the rotation rate at the equator, but those in-between modes, I forget what they're called, sample mid-latitudes. And so by comparing the splittings, the astroseismic mode splittings of those two sets of splittings of the quadrupole modes, you can place constraints on the degree of latitudinal differential rotation. And the punchline of the paper was that they detected 2 sigma and 3 sigma significant detections of latitudinal differential rotation in 13 stars out of like 40. So and none. This is 1 sigma anti-differential and 1 sigma solar-like differential rotation. So most of their sample, 2/3 of their sample, is consistent with uniform rotation. Okay, and none are significantly anti-solar. So that's part of the reason that we think differential rotation is the mechanism that's responsible for driving this transition.
Very interesting. Thank you.
Mark, did you want to ask a question?
Sure. Let me turn my video on. I am a real person. Yeah, so I was thinking about these ideas of how, the magnetic complexity and, the fact that a strong dipole implies a more effective angular momentum loss or faster angular momentum loss. And it occurs to me that the sun, of course, spends sort of half the time with its dipole aligned with the rotation axis, and the rest of the time, during more active parts of its activity cycle, the dipole is not really aligned with the rotation axis. And so in the schematic diagram, like the one you showed from Cecilia Garafo, the sun kind of moves vertically in this diagram throughout every 11 years. So does that introduce, how much uncertainty does that introduce in thinking about the broader picture here? I mean, is that effectively, it means that your mass loss and your angular momentum loss kind of varies with time. Is that, I mean, how well is that accounted for in the story you're telling? I guess that's my basic question.
Yeah, I think, so I think this is what, in part, defines what it means to be a transitional star. Like, this is not something that just happens once and it's done with. It actually takes a while to play out, right? So, and we have relatively few constraints on how long it takes to play out, right? But we know that somewhere between the age of alpha Centauri and 16 sig, the solar cycle might be expected to disappear entirely. But it's already spent a good 1.5 billion years at that point, evolving slowly under this scenario. So it's not that the differential rotation just disappears immediately and the magnetic braking disappears immediately. It's that those things gradually decay on stellar evolutionary timescales. Okay, and in my view, the episodes of like Maunder minimum that we've seen in the sun's past are something that might become more frequent over time as its mean activity level gets lower and lower and gets below, completely below, and always below this threshold of some sort, where you can still drive a cycle sometimes, you see? So I think by its nature, it's a transition that takes some time. Where was that other one? Sorry. Can't remember where the, oh, sorry. Yeah, this one. So we know that the evolution is in the sense that the mean activity level is decreasing over time. And if you imagine that the threshold in this diagram is at 0.15, you know, or maybe a little bit higher, near where the solar minimum level is now, 0.16, then sometimes the sun is in a state that is below that transition and other times not. And then over time, it's going to spend more and more time below the transition and less time above it, right? And so you might expect to see a whole population of Maunder minimum stars where that sort of span that spectrum from always periodic to always constant activity. That's the picture that I've got.
Yeah, and a brief follow-up. So like for younger stars, some of them have more well-defined cycles than others, I guess is true.
Yeah.
So it seems to me that those with less well-defined cycles would always be, or would spend more of their time in a state with higher complexity, and therefore the spin down mechanism would be as effective. And whereas for the younger stars with more well-defined cycles, the spin down mechanism might be more effective. Do you actually, can you tell whether there's a difference in the rate of spin down between those two kind of broad classes of stars?
Well, yes, in some ways. Certainly with the very youngest stars, it's long been known that in young clusters, you have a bimodal distribution of rotation periods, right? Where there are these persistent fast rotators. And they are persistent for longer for the cooler stars. You basically get a peeling away from this fast rotating sequence to the Scumanich sequence in young clusters that starts with the hot F-type stars and then gradually works its way down to the M dwarfs. So that's perfectly consistent with a Rossby threshold at that end as well, where once you hit a certain critical Rossby number at the low end, you turn on a global dynamo. A global dynamo is able to drive the generation and sustain a large scale field that kind of catapults the star into the Scumanich regime completely. And there's certainly evidence from spectropolarimetry that those young saturated regime stars have very complex magnetic fields compared to the Scumanich ones.
Okay, thanks.
Sure.
Junwei and then Sasha.
Okay. Is it possible to determine the thickness of convection zone asteroseismically, and how does the thickness of the convection zone relate to the activity cycles, length of activity cycles, and the level of activity?
Yeah, that's a really excellent question. The answer is yes, absolutely. Astroseismology can, well, at one level, you just match the oscillation frequencies and you have a stellar model. And if you believe that stellar structure model is sound, then you just look up what the depth of the convection zone is. And it does seem to be the case that when you use the actual astroseismic convection zone, the convection zone depths from the astroseismic models, it really snaps into focus the critical Rossby number where this transition takes place in an activity versus rotation diagram. There is an observational method of directly determining the depth of the surface convection zone from the acoustic glitch signature that it produces. They're really hard measurements to make, even with Kepler data, like 4-year time series. But for a sample of a dozen or maybe a couple dozen stars, you can actually measure the acoustic depth anyway of the surface convection zone directly. There's some uncertainties around what that translates into in a physical depth, but certainly it is definitely true that what actually matters here is the depth of the convection zone. No question about it. That is the critical parameter that is driving this transition. So, for example, Kepler observed what you would otherwise call a solar twin, except that it differed in one crucial aspect from the sun, and that is that it had twice the metallicity. And that twice higher metallicity gave it a deeper convection zone, and so it evolves like a cooler star with a deeper convection zone. And even though you might expect it to have exceeded this transition if you didn't know that about it, it hasn't exceeded the transition because it's got a deeper convection zone. So yeah, moving forward, it is definitely our hope that we can combine some of these more detailed characteristics from the astroseismic models to try to understand this transition from the standpoint of convection zone depths.
Thank you.
Sasha, and then Gustavo, I know, has a question.
Thanks, Travis, for a very interesting talk. I actually had a very similar question to Jinwei. And depth of convection zone, it's not just depth of convection zone, but also the energy flux changes during evolution. Luminosity increases, and we have, with some, different convective flux. And it depends how you define the Rossby number. When you said that you define dynamo works in tachocline or dynamo works in subsurface shear layer, and that Rossby numbers are quite different in these two cases. So I think it's a bit more complicated classification of stellar activity. And but the depth of convection zone is not something completely unknown. We have the stellar evolution theory, which is pretty good. So it's in principle, the age, and you can calculate energy fluxes and do more precise classification of observations, I believe.
Yeah, I agree 100%. The difficulty at this point is that we don't have those kind of measurements for very large samples of stars. I expect, a decade from now, after the European Plato mission, which is kind of a super Kepler, after that has been operating for a while, that sample of stars will grow pretty considerably.
Gustavo, and then Nick.
Yeah, I saw a paper by Diego Lorenzo of 2018 or 2019, and he has a picture of activity against age. And it shows that the activity, the relation is pretty continuous. It doesn't show this decay that you have here. And he's working with solar twins. So everything is basically mass, radius, and metallicity are the very same than in the sun. So is there a possibility that these factors are affecting the measurements in some way?
No, you're absolutely right. That is an important study, and it shaped our understanding a little bit. But remember, the discontinuity is in rotation, not in activity. The activity level does continue to decline over time. And you can understand this because you can lose the global dipole field without a disruption in the evolution of activity at all. It won't even notice, right? Because think about the sun. The global dipole field in the sun is the result of a slight imbalance in magnetic flux between the hemispheres that has a mean strength of like a Gauss or something, half a Gauss maybe. Whereas the say quiet sun magnetism has a strength of like 170 Gauss, right? So you get rid of the dipole and the integrated activity level doesn't even notice, right? It's a less than 0.5%. So that evolution is continuous, and that's the other Skumanich relation. And that's good news, because that means that we can use stellar activity as an age proxy continuously throughout the lifetime of sun-like stars. And that's one of the other projects I'm working on right now, is to calibrate that relationship using TESS astroseismic targets.
Thank you.
Nick, go ahead.
Hey, first, thanks for the really nice talk, Travis. That was great. A quick question just related to Junwei and Sasha's question. So going back to this pair of stars that had a deep convection zone and a shallow convection zone, but otherwise they're pretty similar. How similar was their luminosity? Or really, I guess their flux?
You're talking about the Kepler solar analog that I mentioned?
Yeah, where you said one had a different metallicity and a deeper convection zone. How similar was like the surface temperature, or that sort of thing?
Oh yeah, the surface temperature is a little bit different. The more metal-rich star is also a bit cooler. Mm-hmm. Yeah.
But what are we talking? I'm just kind of curious, like ballpark.
Oh, like 100 degrees, 150 degrees. It's not a lot.
Okay, cool. Yeah. Thanks. Just a detailed question.
Yeah.
Are there any other questions? All right, well, thank you so much, Travis, for sharing with us today. I think that I at least learned a lot. And I think based on the questions, everybody else learned a lot too. So let's thank the speaker again. I know he can't hear us, but
appreciate it.